Good evening, Paris. It's great to be here. And I'm Nikhil KURKANI from India. And today I'm going to be talking about how my SVM nailed your malware. This is basically one of our graduation project that we did while we were in engineering, me and my couple of friends. And this was our final year project. And we did a lot of experiments based on implementing the machine learning in terms of the security, and try to see if this could be implemented into the Android malware analysis. So who am I? So as I said, I'm Nikhil from India, and an active member of the null open security community back in Bangalore, and an old school bug bounty hunter, and have been into Hall of Fames of Microsoft, Adobe, Nokia, and a couple of other ones, and currently working as a security engineer at a company, at a firm called Fourth World Security in Bangalore. Okay, so coming back to the agenda. So these are a couple of things that we are going to be covering today, starting off from the introduction, the motive why we try to do this kind of an experiment, and the objectives and the goals, and the method that we use to obtain the motive. Then what exactly are the ways that we try to get this thing working? So one major component was the graph kernels. So implementing graph kernels was the game changer in our situation. Then the next is the whole process, how it was done, and so on and so forth. The last is the SVM, which is how the classification of the malware and the non-malware applications happen. So introduction. So we named it as the Flame framework, which is going to be coming out very soon, which is an open source framework that we have developed. So it's basically built on the open source Python modules for analyzing and detecting the Android malwares. These modules basically help us to extract the call graphs and basically use them to plot the graphs and use the SVM machine to differentiate or classify between the malwares and the non-malwares. So why this project? So some of the obvious reasons why we tried doing this project was because Android being the larger, the major shareholder in the mobile operating system market, and also being the most targeted one. The next is more than 1 billion devices run Android today, and extreme digitization in the developing nations like India, wherein all the transactions are now happening over the internet without all the cashless transactions are happening. And the last would be the existence of third-party application stores that might be still hosting the malicious applications. So what were the objectives and goals? So the first one was to basically check whether the machine learning could be implemented into the Android malware analysis or no. Then build it over a period of time. After we went through most of the failures, we realized that it could be built using a functional call graph method. Then computing based on the similarity between the structured objects. So the main motivation behind the development of this project would be that the malwares cannot modify their behaviors during the time of the analysis. Then it is proactive and fast. Then it's very flexible comparatively, and it could complement. I wouldn't call it as this could be considered as the lone thing to be used for the malware analysis, but it could complement for the dynamic analysis that is usually done. So the success of this model was basically dependent on two different factors. One being the quality of training data set that we provided to it, whether it be the malicious or the non-malicious applications. And the next was how appropriate were these data sets with respect to the classifiers. So the formal problem that we try to solve was that can ML be used in a way to perform Android malware analysis, then trying to find the best fitting hypothesis or a quadratic equation that could make these graphs into labels, and then later on use the SVM to run it across. So we have, say, we have a set of graphs and we have a set of labels and trying to find the hypothesis. So those graphs are to be converted into labels. The traditional machine learning way would be that we are using a graph kernel to compute the kernel metrics, where basically each entry of the I or j corresponding to the graph of I, how similar is it to the graph of j. So this is how traditionally the ML would be done. Then after you compute the kernel matrix, you feed that into a kernelized machine learning algorithm such as the support vector machines. So the whole thing depends on how you are computing the kernel metrics. So what are all the feature space that you're trying to get in for this? So there were a couple of already available models which were used. So the first one being the unsupervised ways models were the k-means clustering algorithm. It ended up having large amount of false positives. And there were a couple of other supervised machine learning algorithms that were used. These different methods had various ways of determining the malicious or non-malicious behavior. So that would include things like determining the traffic from the PCAP files, or using different feature sets such as usage of only HTTP request traffic, so on and so forth. So these were the major ones. So understanding our model in a nutshell. So the APK files, the first thing we would do is collection of the APK files. So right from the Play stores, or be it from the underground market or wherever possible, we would collect the samples. Then they're sent it through the analysis part, where the whole APK is completely reversed into, and it is converted into FCG, which is functional call graphs. And from there on, it is plotted onto a different graph, where the SVM would run it across and see, over a period of time, it would learn to bifurcate between the malicious and the non-malicious. So the training data sets that we used were basically 900 malicious samples and 900 non-malicious samples. So the data set here would be the API call graphs that would be generated, or the function call graphs that would be generated from the APK file that we would get. And this is the prime factor to consider, because that would say whether the new sample that you would give is a malicious or a non-malicious. So parameters that were initially collected were the app name, the application size, the calculated SHA-256, the app type, and the permissions. But these were not the only parameters that could say whether an application is malicious or not. These would come in handy for the initial purpose, but for the later part, the major thing that would come into picture would be the feature space, which would be the function and the API names, and the function and the API calls. So when we consider the basics, if we think like from a programmer's perspective, let's say, for example, Java, which is a procedural language. So everything starts off with a main function, and it goes on moving with various different function calls that are being made to different functions and APIs and whatnot. So let's consider this main function as a root node. Let's consider it in a tree structure. So once we do that, the main function is going to be the root node, and over a period of time, all these other functions become the sub nodes for this main root node. So in that consideration, you could also say that the basic system.out.println is also a function call. So you could consider that. So the main objectives that we tried to do here were these four. The first was the extraction of the functional call graphs, and then labeling the nodes. So once that was done, the hashing and the enumeration was done. Okay, so over a period of, after all these were done, the nearest feature space embedding was again done. We are going to be explaining how these things are done now in the next coming slides. So the last was the learning and the feature analysis. So this was the last part when the whole APK is reversed and sent out to the different modules to make it into a graph, and then SVM learns it. So this learning part, again, comes in handy when you give out a fresh new sample to it. So the phase one, which is the extracting the call graphs. So the functional call graphs that get extracted, it basically contains a separate node for each and every single function of the application. So here we could consider that the function call as the edges and the functions being the actual nodes. So first we got to do that. These are again done using a couple of various different Python modules, wherein the reversing would be done by androguard and a couple of other things. The next one would be the labeling of the nodes. The nodes that are obtained now from the extraction from the call graphs would now be labeled. So the labeling has to be done with respect to its neighbors as well. So it's going to get the labeling based on the instruction set that it contains. The next would be the hashing and the enumeration. So these hash values are again calculated with various different things like XOR and the ROT and a couple of other things. And also it is done for its neighboring nodes. So once this is done, the enumeration has to be started. So once they are hashed, it becomes easy for the graph substructures to be enumerated in a most efficient manner possible. The next would be the explicit mapping, because this is something which is really needed, because we cannot consider the graph structure or say whatever we get from whether the root nodes or the sub nodes or the edges or whatever, those cannot be considered as a mathematical model to be used for an equation. So that way you would explicitly map it onto a graph which would be very easy to get to the final result during the SVM. So the final phase is pretty known, which would take in the concept of SVM, support vector machine, and it would basically run through the different dimensions. This is the thing that we worked on, was running on a multi-dimensional space, because there were many different feature space that were involved in it. So talking about the FCG, so let's consider these three nodes. So don't we think that it is sort of similar to the linked list, wherein we have a node in picture, which is node B, and we have a calling node and we have a called node, right? So this is like a part of the whole FCG that is being considered. So once you see the actual functional call graph, it's going to be really huge. It's going to be multiple number of nodes that are linked together based on the function calls that are being made. So we'll see how this could be again taken ahead. So learning with the graphs. So the main motivation here was to study the relationship between the structured objects. So let's say, for example, let's take in the graph comparison problem, wherein you have a first graph which is G and G prime. So you would see that these are sort of similar, right? And how do you find out, or this is just an example, but in the real world, it's going to be really, really complex. The first and the second images are pretty similar. There would be, the comparison of these would be easily possible by any simple algorithm, but once the complexity increases over a period of time, you would need graph kernels for that. So hence we moved on with the graph kernels. So we actually failed in a couple of things. Initially understanding how this whole thing worked. We tried most of the trial and error methods, finding out different ways to obtain the results, but we literally failed. So the first method that we tried was the base failure Lehman graph kernel, which is very famous and mostly used. We thought we could achieve the results by using this kernel, where we totally went wrong. So what exactly happened was, okay, so this is, okay, for when I say graph kernel, so let me just show you what exactly, okay, my bad. Okay, so when I say graph kernel, so this is a call graph for a very small APK file, so which was reversed, and all these nodes that you see are the various different function, and the lines, the black colored lines, are the function calls, which are the edges. So considering the waste failure layman graph kernel, so the main reason why we considered this was, for us, it was really necessary to see the sorting, the compression, and the relabeling of the nodes. So this was the prime importance for us. So to represent each node V as a sorted list of LV of its neighbors O of M, and then the compression of it into a hashed value, then again relabeling back into a different thing, into a new node label. So these were the primary things that we needed. So once we consider to use this graph kernel, so we also went on to understand how the whole graph kernel works. This graph kernel works. So this is these are its family members, I can say. So the first one being the G and G prime, the second being the subtree, and the third being the shortest path. So looking into it, so first in the G and G prime factor, so first what we would here do is we search for the label functions and then their frequencies, the number of times these have occurred, these different nodes have occurred. And example, let's say G and G prime. So we have these frequency vectors in terms of the functions. So once we are done with that, we infer a dot product to see how similar they are based on the frequencies or the number of occurrences that have been made. So the next one is the KWL subtree of the G and G prime. So considering this, so let me show you the first diagram that we see there on top, the first graph that we see. So wherein you have 4, 2, 3, 2, 3, 2. So the first thing that we would do is we decompose the graph into the subtrees. Then we are going to take each node and then it is labeled also with its neighbor being labeled, and then they are concatenated. So that's what happens in the second diagram that you see there, in the second graph that you see there. So once these are done in such a way, they are put into a table just to map to another label for the compression. So basically we are going to compress the whole 4, 2, 2, 3, 3 into something else such as 11 and put it up there onto a new graph altogether. So once this is done, so we are again going to be comparing the last final end graphs that we would get. The last would be the KWL shortest path. So this basically involves taking the shortest path. So here we are again going to be decomposing the graph into shorter space or the random walks of path. So we here use the shortest path as an instance and then compute the shortest path and take the start label, which is the source node. Okay, and then we go on with the syncing node and then the length of the shortest path, and we compress all of these and bring them into one substructure. Okay, so once we are done with that, so this is how the whole this waste failure layman graph kernel actually works. But this comes with its own drawbacks. So the first being that, firstly, the diagonal dominance problem, which is one of the major problems that this particular graph kernel has, which is there are few graphs or subgraphs which are not identical to any other graphs. So which is a problem. Basically, it won't be able to relate or find similarity amongst others. So it's not going to be taken into consideration at all. So which is a great problem. So secondly, it does not consider the partial similarities between substructures, which means, say, for example, let's take in this two graphs, which is G and G prime. So we see that it only differs by a single node. But this graph kernel is not going to consider it because of this minute difference. Our intuition would say that, considering this would add value to the how reliable this graph kernel would be, but no, it's not going to consider that. So this is one of the major problems. Okay, so one of the next drawbacks that we would see is, so the feature space associated with the graph kernels grow exponentially, which means that, say, for example, for the size of 5, okay, feature space, we would get the graphlets count to say around 50, but once the size goes up to 9, then the number of graphlets you would get is close to 200,000 different graphlets. But once this happens, so I mean, this is the exponential increase that happens. And after this happens, so there would be very less similar graphs or subgraphs that you would see, obviously, which again makes, they won't be able to see any similarity between each other, and they would think that, okay, so this is not going to work out, and the graphlets won't match, and you would obviously get that things are not malicious or not malicious. I mean, you would obviously end up getting the wrong results. So the next method that we thought was of using the neighborhood hash graph kernels. So this is also called as the Hido and Kashima method, so which is quite known, well known. So in the generalized way, I could say that, say let's consider the original graph, which is node A, node B, and node C. And so the second graph that we see here is basically replaced with 4-bit labels, which is hash 1110, 1000, 1100. So how are we getting these hashes made is basically, again, a different story, which involves the quadratic equations and a couple of logical operations such as XOR and ROT, which are basically performed on these bit labels. So one of the major reason why we thought of taking this Hido and Kashima method was for the matching coefficients, then sort the hash values and count the common labels, then computing of the coefficients. So this was one of the prime reasons that we took. So again, coming back to the same functional call graphs obtained. So this call graph was actually obtained from the Hido and Kashima method. This was an APK file which was not even larger than 50 kilobytes. So imagine, if you could, run a scan through for a really big APK file. So the amount of nodes that you would see is going to be humongous. So the analysis of, again, APK was taken very seriously. So what we did was we tried collecting all the samples from various different places like the Contagio dumps or the Google Play Store or whichever way possible. And we first ran all of these through the VirusTotal website and saw whether these were really malicious or not. So the ones that were termed non-malicious were kept separate, and the ones that were termed as malicious were completely kept separate. So these became our training sets. So once we got our training sets ready, we went on with running the reversing part, which was using the AndroGuard. So that, again, over a period of time, with using a couple of other modules, again, we were also able to extract the API calls that were made. So considering all that, let's see the modules and dependencies that were involved in making this. So all of the things that we used were very open source. So the AndroGuard, which was used for reversing, the NetworkX, which was used to make the graph, and then the matplotlib was to basically plot onto the final graph that was obtained from the frequency obtained or the histogram. Then the next one was the NumPy and SkyPy. Then the scikit-learn, and there was a module for the SVM, which was libsvm, which comes under the Python itself that we used. And last was the cpkl. So these were a couple of dependencies that we depended on. So considering the use case diagram, so this is how we could consider that the user inputs the APK file, it goes to the AndroGuard, it gets reversed, then you get the manifest description and a couple of other things. Then you also get your different API calls and everything else. Then it goes to the NetworkX, which again is used for the functional call graph mapping. So once you're done with getting the functional call graphs, you would run it through the scikit-learn for the machine learning, and you would get the segregated malicious or non-malicious APK files. Yeah, considering the support vector machine, which is like the hero in this scenario now. So we'll do it the SVM way. So this is just a two-dimensional space that I'm showing here, wherein you could easily segregate the malicious as the ones that are on the top, and the non-malicious are the ones that are on the bottom. and this plane cuts through, which basically classifies which is malicious and which is non-malicious. So, okay, so this is SVM 101, very, very basics for people who didn't know what exactly is SVM. So, how do we do it? So, one thing, we could cut the plane in any of the ways, basically to segregate the malicious and the non-malicious. So, you could see the way it is classifying it. So, you could also see you could also draw another SVM plane that would come in this way, or you could also see it coming up in this way. Okay, so the points that you see at the edges is basically what matters, which are going to be the support vectors for us. So, but there is a catch here. There is a possibility that sometimes you would get a misclassification. So you might end up seeing a malicious file coming under a non-malicious segment, or a non-malicious file coming under a malicious segment. This happens basically because of the margin or the padding that we provide. Okay, but over a period of time, as the machine learns on its own, I think that could be overridden. But this is the reason why the whole machine learning process could not be taken as a 100% thing. So again, the defining of the margin is left to us. So you could again go ahead and maximize the margins that you can see. So the things that you can see there, the support vectors are nothing but the data points that the margin pushes up to against. So that is the place, or those points are the ones that are considered as the support vectors. So the main thing here is that the classifier here is separating a separating hyperplane. So this is just a basic symbolizing of how this SVM would have worked. But because we took in a lot of different feature spaces, so right from the function calls or the API calls that were made to the names or the file names or the file sizes or the various different other factors, it ended up being, it's a multi-dimensional array that we were able to get, and running an SVM through it is a really big task. So what were the final results that we were able to obtain? So this was basically the confusion matrix. So we were able to get, so out of the 900 different malicious and the non-malicious files that we provided, so this is what we were able to obtain, wherein 750 of them were true positive. So we got a false positive rate of 27, which was a pretty decent one, pretty good, I can say. And false negative was 60, and true negative has been 850. So you could say that the accuracy for this was 78%, and the false positive rate was 3%. But this was again done on only 900 different set of malwares. So which means that we still need a lot of malwares for this to be considered as an effective model. So this was how our process basically started. So we started off as a college project. So we went on with the various different things like the data analysis. We did a lot of research. We talked to the experts in the industry back in Bangalore. Then we took help of the community back in Bangalore, which is the null security community. And we did improvise over a period of time on the number of feature spaces selection, which is the primary importance in this project. And over a period of time, the development happened. Then we also try to understand the industry standards, and we are going to be launching it very soon. And it's going to be completely an open source framework. And the conclusion finally. So machine learning algos could be used for malware analysis, but only as a complementary feature to the dynamic analysis. I mean, that's what we felt. So probably this would, again, change our perspective over a period of time as years to come. getting feature space right is indeed a big deal, because you never know how a feature space might turn your whole process into a negative side, and end up giving you wrong results. The next would be is that, I mean, this is real. It actually needed a high computation speed and processing power to run this basic SVM on the APK files. We tried it on our systems. It never worked. We had to buy C4X large on Amazon AWS and run it on them. So that's when we were able to run it in a proper way and get things done, working. So these models can be generalized to most adwares with a few extra features, but it would need some more research on them. And yes, so it still has got a couple of drawbacks in terms of considering what kind of obfuscation level that this would be able to dethrow, whether it be the obfuscation at only the functional calls level, or being the classes, or the different obfuscation levels that are usually there. So this was the team that actually worked behind this. So we were a bunch of college friends. So this was our final year graduation project that we did. And so that was about the project. And these are a couple of references without whom I'm pretty sure it wouldn't have been possible. Because we actually based out our experiments on different research papers that were already made. Because we ended up losing a lot of time, wasting a lot of energy, and making a lot of mistakes and failures, which shouldn't have been happened in the first place. But again, these are all the papers without which this wouldn't have been possible. And I guess I can show a small demo on how this project would look like once it's up and running. Okay. So this is the basic framework that you could run it on your servers or your cloud platform. So once you basically log in, you would see the screen. Okay, so once you get into the dashboard, so this is how it looks. So we have already scanned a couple of files, so which is file scan were 55, and out of which 26 were non-malicious and 29 were malicious files. So an user could be easily possible to go on and upload an APK file either on his phone or on his system. Yeah, so we go to the dashboard, we upload the file, the APK file, and let's see what it gives back. So to test again the authenticity of this project, we did again take in a different set of malwares and the non-malicious files. So again, here we have a set of clean files and a set of infected files. So we tried checking it. So these were completely different from the real actual, the data sets that we had given in the initial stage. So we still are working on this. So yeah, it's going to be able to show the results now. Yeah, it proved out to be a non-malicious file. We still are working on the confidence level at which it would say that a particular file is malicious or not. So that is what we are trying to still implement into this. And yeah, for sure we are releasing it very soon, and it's going to be completely open source. So again, we are going to be trying it out with an infected file and see how it works. Okay, it turned out to be a malicious file. So the main concept here for us was that, to see whether this could work out in a very feasible manner, because the amount of time and money that went through in buying a C4X large Amazon AWS was hilarious. When we told our whole university to go on and test out your APK files, the next day when we opened up our AWS console, we were really shocked to see the amount of money that we owed them. So we are still working on that, and we're trying to see if this could be, again, if there is any way to optimize this method, and also to see if this could be again enhanced in trying to tell at a very confidence level of whether this particular app is a malicious or not. So I guess that was it about from my side. So any questions, I'm really free to take. Thank you. Yeah.
Hi, thank you for your presentation.
Thank you.
I have a couple of questions about the training of your classifier.
Okay.
How did you get your dataset?
Huh?
How did you get your dataset? How did you generate it?
The data sets. So
Yeah.
the data sets were basically taken in from the infected files or the normal files. The normal non-malicious files were taken directly from the Google Play stores,
Yeah.
and the infected files were either taken from a couple of different sites like Contagio, Dumps, and a couple of other places.
Okay, and another question about the classifier. Did you try the neural network systems?
Exactly. So we did really, we started off with using the support vector machines. Then over a period of time, we also saw that this could be implemented with the neural networks with the combination of natural NLP, which is natural language processing and things like that. But the time amount that we had to submit this project was very less. So that's why we thought, let's go on with the SVM and see over a period of time if we could enhance this thing into the neural networks. Any other questions?
First of all, I would like to thank you for this talk.
Thank you.
My question is about the computation level. You said that in the conclusion that when we are creating the model, we need a lot of resources.
Computation power, yeah.
I would like to know that after the creation of the model and after the deployment, would the user need this level of performance in order to use the application?
Yeah, so with this current model that we have got, so it was running flawlessly on Amazon AWS C4X Large. Anything below that, it had a bit of a lag. Okay, so that's what we saw. So the amount of time that you saw here was pretty, okay, I wouldn't say pretty quick, but comparatively it was way actually better. But when you take a T2 micro, or T2 micro is very less. So T2 micro would probably take you a day probably. You would always see that scanning, rolling thing going on. So, we are trying to, bring it down. We are trying to work out different ways. But let's see if it comes out, once we push it out as an open source project, we would see plenty of people coming in and supporting this. And it's going to be really great. Any other questions?
No.
Thank you very much. Do we have any questions? Everything was clear? Okay, very nice. So, yes, I will let you conclude. You have more conclusions to do? Okay.
So I guess you guys have been a great audience, and I would like to thank the team, the NDH team, and everyone else who's been part of this conference. It's been really great coming from India to here to see the whole new world. And thanks a lot, guys. Thank you very much.
Thank you. Thank you for coming.